Welcome to Stage 2 of the VoskenAI platform. Stage 1 turned a brief into 35 formal, testable hardware requirements. Today, we see how those requirements feed directly into Stage 2 to produce a complete system architecture automatically.
Architecture is where the most expensive mistakes happen. A wrong protocol choice, a missed clock domain crossing, or a forgotten requirement will propagate all the way to silicon. VoskenAI eliminates these failure modes by making every decision explicit, traceable, and reviewed by a specialized AI crew before it is committed. Stage 2 takes one structured JSON input and produces 4 validated outputs. These include the external interface spec, subsystem architecture, register map, and clock/power plan. This forms the complete blueprint that every downstream stage consumes, all produced in a single automated run in under 30 minutes. Stage 2 is a pipeline of 6 specialized AI crews. Each crew receives only the context it needs, plus the outputs of the stages before it. Dedicated reviewer crews, completely separate agents, can only analyze, never modify. Stage 6 integration is pure Python code, guaranteeing structural correctness of the final output. The Create, Review, Revise loop is the same quality engine introduced in Stage 1. The reviewer cannot modify and can only find findings. The reviser can only fix what was flagged and cannot invent new structure. Issues known to be acceptable are passed forward, preventing the system from getting stuck in endless loops. The interface architect starts by reading every requirement and identifying every external signal. It queries the protocol library to assign protocol IDs, ensuring consistency from Stage 2 to Stage 6. Every decision references the requirement IDs that justify it, providing full traceability. The subsystem decomposition is where the block diagram is born. The AI system architect follows the functional boundaries implied by the requirements to create clean partitions. The reviewer checks the decomposition, looking for missing interfaces and ambiguous boundaries. Issues are tracked persistently across all remaining stages. Protocol selection for internal interfaces consults the protocol library, enforcing consistency with the anchor and propagate rule. Clock and reset planning explicitly models every clock domain, every crossing, and every reset strategy. For complex designs, this is where clock domain crossing bugs are caught before any RTL is written. The Register Designer agent produces machine-readable register maps with every field fully specified. This is critical because an undocumented side effect or incorrect access type can produce driver bugs that are hard to debug at the system level. Software hazards, like read-modify-write risks, are flagged in the documentation. Step 6 integration is pure code, guaranteeing structural correctness of the final output. The design intent document records every architectural decision at the moment it is made, with rationale and requirement reference. This auto-generated traceability provides the complete intellectual history of the design for every stage. The quality gate is a deterministic pass/fail check using a Python validator, running after integration. It checks for things like uncovered requirements, missing policies, invalid protocols, and undocumented decisions. A critical finding anywhere blocks progression until the issue is resolved. Now let's walk through the AXI timer as a concrete example. All the flows we discussed, the 6-stage pipeline, the protocol library, the review loop, and the quality gate, were applied to this real 32-bit AXI Timer IP. Here is the complete block diagram that Stage 2 produces. It has 2 subsystems. Subsys CTL handles software-facing elements like the AXI interface, and Subsys TMR handles the timer data path. This topology is now frozen and becomes the input to Stage 3. 6 logical interfaces were defined, each mapped to a protocol ID from the library. The AXI4 Lite interface expands to 15 physical signals. The agent automatically generated this list, as the protocol library knows the full signal list. Every interface carries a requirement reference for instant traceability. The register map for the AXI timer has 4 registers and 8 fully typed fields. The agent resolved a gap from stage 1 by fixing the clock using the clock enable model. Everything runs on the AXI clock. The external reference clock feeds a 2-flop edge detector to generate a clock enable pulse, resulting in 0 clock domain crossing paths. VoskenAI detected that a naive 2-domain design would conflict with the performance requirement. The CRP planner resolved this by selecting the clock enable model. The counter runs entirely in the AXI clock domain, with the timer reference clock only generating a single-bit enable pulse. This eliminates multi-bit clock domain crossing, reduces formal verification scope, and guarantees latency requirements. The quality gate for the AXI timer passed all checks, 0 failures. 35 requirements in, 35 requirements covered. This is a deterministic pass, providing a final safety net before the architecture is handed to stage 3. Traditional system architecture takes 3 to 4 weeks of senior engineer time. VoskenAI completes all of that in under 30 minutes. The output is more complete, with every requirement covered, every decision documented, and every protocol validated. The Stage 2 architecture object is the complete input to Stage 3. The subsystems become the starting points for recursive decomposition. The register map and clock domain plan constrain timing at every level, and the design intent document continues to accumulate knowledge through all 8 stages. 35 requirements processed by 7 AI crews, resulting in 6 external interfaces and 2 decomposed subsystems. 100% requirement coverage, verified deterministically, all in under 30 minutes. This is the complete, validated, traceable architecture blueprint delivered by VoskenAI Stage 2. Stage 2 of the VoskenAI platform transforms formal requirements into a complete, validated architecture blueprint in under 30 minutes. It's ready for Stage 3, producing subsystem architecture, interfaces, register map, and clock plan automatically. Thank you.